Before 2010, computer viruses were understood to be digital problems. They were tools for stealing data or locking screens for ransom, but their consequences ended at the edge of the monitor. Critical infrastructure was protected by the air gap, a total physical disconnection from the internet. If a machine isn't connected to the outside world, the logic followed, it cannot be hacked. That security model lasted until June 2010, deep beneath the surface of a highly secured facility in the Iranian desert. Inside the Natanz enrichment plant, rows of precision industrial centrifuges began failing at an alarming rate. These machines are engineered to spin at incredible speeds with total stability, but suddenly they were vibrating themselves to pieces. The engineers assumed the problem was mechanical wear or a flaw in the metal. Software was never suspected because the system had no path to the outside world, but code had successfully bridged the gap. It marked a transition where digital instructions could achieve the same physical results as an explosive, while leaving the facility completely silent. Physical isolation provides a sense of security, but it remains vulnerable to the humans who must interact with the machines. The malware reached the inner network on a standard USB drive. An unwitting worker carried the drive past the armed guards and the perimeter fencing, plugging it directly into a workstation. There was no need to bypass a remote firewall or crack an encryption key from across the globe. The security of the entire compound was bypassed by a routine, everyday task that brought the weapon directly into the heart of the system. Unlike a typical virus that spreads to as many computers as possible, this malware was programmed for restraint. It was designed to stay dormant. Once on the network, it silently scanned hundreds of internal digital nodes, looking for one very specific environment. It only executed its payload when it identified a specific Programmable Logic Controller, or PLC. If that exact setup wasn't present, the malware did nothing. It was a precision-guided weapon built with the patience to wait for its singular intended target. Once the target was confirmed, the malware began subtly overwriting the operational commands, forcing the centrifuges to spin at speeds they couldn't handle. Normally, sensors would detect this and alert the control room. To prevent this, the malware began intercepting the machine's outgoing reports. This schematic shows how the deception worked. While the machinery was physically failing, the malware blocked those signals and sent a fake loop of normal data to the engineers' monitors. On their screens, the facility looked calm and stable. The code was designed to blind the operators, making them spectators to an attack they couldn't even see. The attack created two simultaneous realities. On the factory floor, there was catastrophic mechanical failure. In the control room, the monitor showed a perfectly functioning facility. The engineers were trapped in an illusion of control. They were watching the machines report their own health, even as they were being dismantled from the inside out. This satellite view of Natanz shows the extensive perimeter fencing and guard stations designed to keep intruders out. But the code demonstrated that these physical barriers provide no defense against a weapon that arrives on a thumb drive. It proved that an air gap is only as effective as the discipline of the people who work inside it. In the end, roughly 1,000 centrifuges were destroyed. The operation proved that a line of code can be engineered to sabotage heavy industry from within, leaving a screen to report that everything is completely normal until the damage is irreversible. For decades, computer viruses followed a predictable set of rules. They existed entirely within the digital realm, designed to steal data, infiltrate mail servers, or crash operating systems. Achieving physical destruction historically required traditional kinetic weapons. There was a clear separation between the bits of data moving through a network and the steel gears of heavy machinery. A covert operation, never intended for public discovery, proved this separation was an illusion. The weapon was designed to hit an air-gapped facility, a system physically disconnected from the internet. It relied on infected USB drives to bridge that gap, but the code eventually leaked back onto a technician's laptop that reconnected to the web. The malware had escaped. When cybersecurity researchers captured this rogue code in the wild, they initially struggled to categorize it. The file was 20 times larger than a typical virus. It was a massive, densely layered piece of software that seemed to be hunting for one specific hardware configuration. The resources required to build a weapon of this complexity pointed directly toward a nation-state's intelligence agency. Analysts began reverse engineering the code, realizing it was an unprecedented piece of digital engineering. The code used 4 simultaneous zero-day exploits, targeting unpatched vulnerabilities unknown to developers, to bypass security silently. It also used stolen digital certificates to identify as trusted software, operating deep within the network without triggering alarms. Obtaining even one zero-day exploit is an expensive, difficult process. The presence of 4, combined with stolen certificates, confirmed this was a government-funded project. Specific instructions hidden within the code eventually directed investigators toward the Natanz nuclear facility in Iran. The malware, now known as Stuxnet, was linked to a joint US-Israeli campaign called Operation Olympic Games. The software was engineered to take control of industrial frequency drives. It worked by forcing the facility centrifuges to spin at dangerous speeds, causing the rotors to vibrate until they physically shattered, all while reporting to the operators that everything was normal. The successful sabotage at Natanz confirmed that software could now be used to destroy physical infrastructure. Once Stuxnet leaked into the wild, the blueprint for digital sabotage became public knowledge. Governments worldwide responded by rapidly expanding their offensive and defensive digital capabilities. Stuxnet demonstrated that a line of code could achieve the same results as a targeted airstrike, adding a new, invisible layer to international conflict. The battlefield now includes the interconnected domestic systems we rely on daily. National electrical grids, essential for modern life, are now vulnerable to targeted digital disruption that can bypass traditional borders. This new reality also affects healthcare networks, where a breach can disrupt life-saving systems and patient care. Major transportation hubs face the threat of logistical paralysis if their centralized control systems are targeted. The next major conflict may not begin with a physical explosion, but with a silent execution of code. Understanding how this technology works is no longer optional, it is a requirement for our security.